Rafayel is talking about optimal design problems ruled by fractional diffusions.
Thank you. Thank you. First I want to thank the organizers for giving this opportunity to be here with these great specialists. And this is my first time in Rio, and this is an opportunity to see the Rio. I've been in Brazil, but I spent 1 year in University of Fortaleza, Federal University of Ceará in Fortaleza, and where this work with joint with Eduardo Teixeira was born. So before going to the explicit, concrete statement of the problem, I just want to write vaguely what do we mean, what are we trying to do. We are given, suppose we have a nice function which is going to be non-negative. In fact, sometimes we need this function to be strictly positive in a set with a measure, Lebesgue measure, non-zero, positive Lebesgue measure. But let's say, okay, non-negative function. And we are given a domain. We try to solve this function, this problem. So we're trying to find the alpha harmonic function which agrees with phi outside of the domain and has the prescribed given fixed volume of positivity set. So the Lebesgue measure of the positivity set is going to be fixed. This is also given. These problems has many motivations, but as you see, I mean, maybe it is worth it to write the definition of fractional Laplacian, although many people already talked about it. I'll have it written here. So this is how we define it. And so this is a constant. Local versions of this problem were studied by many authors. Like the original work begins again with Caffarelli, Aguilera, Caffarelli, and Alt. I guess it's in '86. They do it with Laplacian. So they're looking for harmonic function with a given prescribed boundary datum and the prescribed volume. Positivity, volume of positivity set. Then later, this theory was improved in a bit larger class of operators. I guess next work in this area was in more or less in '05 by Danieli and Petrosyan. They do sort of P-Laplacian, but it's a bit different. The P-Laplacian case was discussed in the paper by, I guess, Bonder, Martinez, and Volansky in '06. Then there is a paper by Eduardo Teixeira, I guess this is going already out in 2010, where he deals with a large class of divergence form operators. And again, the ideas they use in all of these cases are the same. The technique is the same. Some adaptations are done, of course. So what makes this different from the previous cases? First of all, this is a non-local already. And what is common in all these cases, we are dealing with the divergence type operators. Here we have something not really nice. No, it's not ugly, but it's not very pleasant, no? We are, then there is one more work which was very helpful in our studies. That was a work which is different. It does not have a volume constraint, but it's different, different problem, but the techniques are really helpful. That's going to be Caffarelli, Roque Joffre, I guess, and Yannick Sidi in 2010. They are dealing with a problem already involving fractional Laplacian, but it's different problem, but they are giving us the tools how to work in our case. So we are going to try to adapt the techniques that we already know to this case. For that, we would like to work with the divergence type operators. And here again, we use a result by Caffarelli and Silvestri. This is a sort of an extension type argument to transfer the tools used here to our framework. So let me start by the concrete definition of the problem. So we are trying to minimize the functional, this is sort of fractional Laplacian, over the set with a prescribed positivity, volume of positivity set and sort of boundary data. Okay, so there are two difficulties. We want to deal with a divergence type operator, and we want to make it sort of local. We want to deal with the local values of the function. We want to how we proceed. The idea is exactly the same as in the previous cases I mentioned before. We try to add a penalized parameter here, minimize that one. The penalized parameter is going to, like this condition, we are going to include there. The idea is that the minimizers of penalized problems, imagine here is the penalized parameter, some beta epsilon or f epsilon. The idea is that for some values of epsilon, when epsilon is very small, the optimal configurations will prefer to pay this volume, this charge, than not to. Yeah. So this is what I was just talking about. So we are following still the ideas of the previous works. We're adding a penalized parameter here. The penalization is given by this explicitly. So it's charging for the values which exceed the volume. And we are going to try to, we hope that it's easier to work with this, and then we transfer the properties to the original problem. So this is our penalized problem. We're looking for a function which minimizes over this set, this functional, with the penalization term. Here, this is an extension argument I was talking about by Caffarelli and Silvestri, how to transfer to divergence type operators. Just I'm going to draw here something about just for a half Laplacian. I guess most of people here already know what I'm going to talk about, but let me just, for the sake of completeness, write down here what are we doing. So if you look at the half Laplacian here, turns out it's you are solving something like this. So you look at one dimension higher, you solve harmonically, you continue. So you have a boundary values here. You solve this Dirichlet problem, right? Suppose something like this, right? And then when this is, we can write the solution explicitly, right? Poisson, and then turns out when you count this, this gives you exactly the half Laplacian. What's better here, because here is already gradient, the derivative. So Caffarelli and Silvestri continued this argument for any alpha here. I mean, not just half. They found a way how to continue in one dimension higher to have similar result. This is what is written here. So you go one dimension higher, you solve this problem, then turns out the fractional Laplacian is this limit. And this is already nice because, okay, you continue evenly because you already are dealing with something with a divergence here. And this already gets us closer to the previous works. And the work I mentioned here, that's very important, but is not exactly what we were doing here. The technique is here. So how now the penalized problem we had here, so we can do the extension argument instead of this to write something with gradients instead of the first functional. That's what we do here. So we define an appropriate space. We do this extension argument, and the first part of the functional, the energy term, has this expression already. It has some weight, but this weight is not too bad. And then our usual penalized term already. So our problem, the penalized problem, becomes already now this. So we're minimizing, we're looking at for the local minimizers of a function, of this functional that satisfy this. So there are local minimizers in this set, in this H1 that we defined. This is the technique used in Caffarelli, Roquejoff paper. So this is already a bit nicer. Instead of the whole space, we have omega here, and we have a divergence type expression here. How we continue here? We were able to show some properties of solutions. The proofs are more or less the same. The ideas are the same as were done in the previous cases. I'll mention some comments and emphasize the differences, what differ from the previous cases. So the first one is it exists. So there is a solution. And the proof is, as is done usual, we take a minimizing sequence, look at the limit, and that's what it is. That's a minimizer. And the second one, we show the Holder regularity of the solution with the exponent alpha. So this is the maximum we can get. We have no hope to get more than alpha, right? This is the optimal regularity. I'm going to talk a bit about this later. We show non-degeneracy property. The proof is, again, with the same ideas. We assume this is not true. We construct a function where we get a contradiction with the minimality property. So as a consequence of the Holder regularity and non-degeneracy, we are able to show some positive density results, which we may use later. The Hausdorff dimension in -1 dimensional Hausdorff measure locally is finite. This was actually discussed or proved in the recent work by De Silva and Savin. And also, there is this kind of asymptotic behavior with a q epsilon x0. And later on, actually, we see that this q, in fact, does not depend even on the point. It's a constant. Depends only on epsilon. I'm going to talk about the proof of this later. If you imagine here, nu being this is the normal, of course, being the n directional normal coordinate. So this is going to be the
Rafayel?
xn.
Rafayel?
I'm sorry?
You have a question.
Are these uniform in epsilon?
No. Yeah, I forgot to mention yet. Every constant you see here may depend on epsilon. Yeah, but this is a bit, we don't like it, of course, but the thing is, in this kind of problems, that epsilon never goes to 0. It remains always fixed. It's very small, but it's fixed. So there is no, we don't afraid that something is going to blow up. And yeah, I'm going to talk. So this is basically means that the blow up limits are one-dimensional. That's what I was trying to say here. I'm going to talk about the proof of this later, which was basically done in this paper by Caffarelli, Roquejoff in Siri. Can be found also the book Salsa Caffarelli. Okay, so I'm proceeding to the proofs. For the Holder regularity, we're using this characterization of Holder functions. So we basically show that the solution satisfies this inequality, so it is Holder. how we do, again, we proceed as the tools provided in this recent work. So we consider the harmonic replacement of u in the ball. So then immediately we have this inequality. So if you remember, the functional was this plus some penalized parameter, and the same here. So we have a constant c here which depends on epsilon. But as I said, that does not bother us. And then I tried to put all the steps of the proof in one slide, so I'm jumping a bit here. If you play a bit with this term here, you can actually show that you can get rid of this. I mean, you put another constant here, but you can write this. And this, if you look carefully to the characterization, as I mentioned in the previous slide, this is exactly what we want. When beta is positive, beta, let me remind, beta was 1 minus 2 alpha. And since alpha is a fraction in 0, 1, this belongs to minus 1, 1. So it can be negative and positive. When it's positive, this is the characterization theorem with a P1. When it's negative, the same with a P2. So this way, we have Holder regularity. I just want to remind that we are talking just about the penalized solutions of penalized problem, and all these solutions depend on epsilon. I just don't mention an epsilon here for not to be too heavy on the notations. And then, as I told before, I'm going to talk about a bit about the fact that one-dimensional, the blow-up limits are one-dimensional. This is how we define the blow-up. So we want to see basically this. And this is, again, an argument in this paper by Caffarelli, Roquejoff, and Siri. They show that, OK, you can find a suitable coordinate system. And then here, if you look at this function v, you look at this relation between u and v. This first inequality is the non-degeneracy property. The second inequality is the optimal regularity property. So if you look at the relation, the oscillation lemma, which still remains valid for this fractional case, there is a lambda, which is this is important, which is invariant, remains invariant under this blow-up scaling, for which this inequality holds. And since you can continue all the way around, and this lambda does not change, the only conclusion is that the relation should be constant. The oscillation is 0. So far I was talking about some properties of penalized problem, and here I'm going to talk about so-called Hadamard variational formula, which allows us to transfer all these properties of solution of penalized problem to the original problem. So the idea is this. So we are trying to do a perturbation inward or outward, so something like this, and then compare the configurations, the optimal configuration, to see how the functional is changing, to have some control over the penalized parameter change and the integral term of the functional, how they change. The local versions of this were known for many years, were used and proved actually in some cases in this paper for particular cases. Now, what we do, we do similar perturbations as in the local cases. So you see it looks ugly. So we want to change the volume by V and see how the functional is changing. And we are going to need to use change of variable formula. So the Jacobian comes out. It's a heavy computation. That's what I'm trying to say. I didn't do anything here. I'm just write the conclusion, what we get. So if you do all these, you do all the computations. Yeah, I forgot to mention with the configuration we want to compare with. So this is the configuration. We are going to try to compare our functional over VR to functional over U and see how it changes. And this is the result. So the change in this part is like this. So there is a constant, This actually is the constant I talked before, that here maybe it's worth it to go back. There was this constant here, yeah, depending on x0. This is on regular points. It turns out to be constant, so it does not depend at a point at all. So this q epsilon is our lambda epsilon, now fixed, so it does not depend on the point anymore. So as I was telling, so this is the result we get. We get something of this type, which allows to transfer the properties of penalized problem to the original problem. This is where I'm going to talk soon. Okay, how we do it? The constant here that appears in Hadamar's formula depends on epsilon, but turns out it is possible to estimate from above, from below, with a constant independent of epsilon. The proofs are similar. Like this one is sort of mean value property. This one is using Hopf lemma, which has a fractional. It's true for the fractional Laplacian too, fractional analog. The next we say, okay, what is remaining to check? Like if the volume is attained for some epsilons, for small epsilons, then we can say we're done, right? Then our functional does not have the penalized term anymore, and what we are dealing with is the original problem. And so the properties we know already for the penalized problem transfer to the original problem. So we say, okay, let's say this does not hold. So the volume is not attained. So let's say it's large or small, and we find a new function putting in between. So having still the volume of positivity set being larger if the original one is larger, then we compare the penalized part, since by the choice of u tilde we have this exactly equality here, and this v is the change of volume we do. Then we are using the Hadamard here, and then this estimate from the first step. So this c already does not depend on epsilon. I'm using it from here. But then when you put this together with a minimality property of u epsilon, you get this inequality, which gives a contradiction when epsilon is smaller than this number. So the volume cannot be bigger than omega. The same way it cannot be smaller than omega, because we have also a lower bound. We have again Hadamard. We get another contradiction, so that ends our problem. So that we can say that all the properties we're talking about for the solution of penalized problem are solutions of the original problem. So they hold the same properties. They are Holder regular and degenerate and so on. I guess this was all that. Some literature that I was referring to. This is a concrete reference now here. This is the work, the earliest work. I guess there is a similar work in 1981 by Alt Caffarelli. This is sort of continuation of that. The one I was referring with the P-Laplacian case, Bonder, Martinez, Volansky in 2006. And then there is this paper which gives us lots of tools to work with. Danieli, Petrosian, they discuss in this paper a bit different problem, but the technique they use, the adaptations they use are very helpful to continue, for example, in this paper and so on. And this is a work I was talking about that deals with a large class of divergence type operators. And this is the current work I just talked about, the reference. So this was all. Thank you.
Thank you, Rafayel.